Alrighty, we are going to get started with the last section of the Chapter 2B chapter. So it is 2.6b. It's analysis of rational functions and their graphs. And it's just going to really help us piece together and make more connections with our rational functions. And it's really going to help us process what we did in the 2.6a lesson as well. So 2.6b. The first example asks us to find the equation of the asymptotes. So instead of us having to take an equation and find them, we can find them from the graph, or we can find them from the equation too, because we have one. Well, we know the best thing to do is to always factor. So you can probably see these from the graph as well. But I just want you to see it here too. So vertical asymptotes are going to be x equals negative 2 and 2. Horizontal asymptotes, so we need to do p and q. Before we do this though, I want you to take a different approach just for a second and think of this for a horizontal. As the x's are getting larger, what are the y values approaching? Are they going to infinity, or are they converging to a number? So if you look at this, these are getting closer and closer to the number 3. And then if it's the same number here as x is going to negative infinity, it's also approaching 3. So our height of 3 is what our horizontal asymptote is. So let's just see if our p's and q's confirm that. P and Q are each 2, so they're equal. So then we do the ratio of their leading coefficients, and we get 3. So that's true. And there is no slant because P is not greater than Q by exactly 1. Okay, next one. You might want to try on your own this time. Pause the video and see if you can pick it up. You can kind of see where this asymptote is, right? Let's see. If we factor this right here, I don't think we can factor the numerator, but the denominator would be 3 times x plus 2. And that's kind of written on the words, but you get it. So our vertical is going to be x equals negative 2. And then horizontal. So we do p and q, but also super interesting. Gosh, I'm such a math nerd. Are they converging to the same number? So as x's are getting larger, this is going to positive infinity, and as the x's are getting smaller, it's negative infinity, which means it's actually not converging at all because you can't equal infinity ever, but it's not approaching the same number. So let's see what that does. So P is 2 and Q is 1. Again, I'm looking at the highest powers or the degrees. P is greater than Q, so there is none, but there is a slant. And to find that slant asymptote right there, I am going to use long division. So I'm going to take 3x plus 6 and put it into x squared plus 3x minus 2. And then do my little math over here because I think there's going to be fractions. So x squared over 3x would reduce to 1/3 x. Then that would give me minus x squared. And 1/3 of 6 is 2. So then I'm going to get x minus 2. And then I have x over 3x, which is 1/3. So I get that, and then I get to disregard the remainder. So y equals 1/3. Maybe if I keep my knuckle out of the way, you guys can see, plus 1/3. Is that better? Hopefully. I'll try. It's weird to write that way, but anything for you guys. Okay, next one right here. Vertical asymptote is going to be the same as the previous problem because it's the non-canceling factors. And since this graph has no holes, I know it's a non-canceling factor. So x equals negative 2. And then the horizontal asymptote, we're doing that p and q again. 2, 1, greater, none. And then the next one is the slant. So we have 3x plus 6 divided by negative 2x squared minus 2x minus 2. So negative 2x squared over 3x is negative 2 thirds x. So that's going to give me minus 2x squared. And then this will be 6 times negative 2 is negative 12 divided by 3 would be minus negative 4x. So that would be 2x minus 2. And then I get 2x divided by 3x. So that's plus 2/3. So y equals, don't just write the part, you need the equation, which means you need an equal sign. Alrighty, so there's that piece of it. That was pretty straightforward, just probably a little bit of a review with some fractional slant or oblique asymptotes. And now we're going to move on to example 4. So example 4 says, consider this function. So you guys know I'm going to put tricky on this. I think you should definitely study this. Maybe if it's a flashcard, you're going to divide it up into 2. Like you can label this A, B, C, and then D, E, F, or something like that. So first thing I'm always going to do with these rationals is factor. The bottom's easier for me to factor because of that difference of squares. Ah, look. Okay, so it cancels. So step 1, what is the equation of the function in completely factored form? So that's f of x equals x plus 3 over x plus 2. If any exist, identify the vertical asymptotes. X equals negative 2. How do I know? It's a non-canceling factor in denominator. Okay, in denom. You need to have that. Does the function have any holes in the graph? Yes. Explain why or why not. Yes, because x minus 2 is a canceling factor. You don't have to write in the numerator and the denominator because it can only be a canceling factor if it's in both. So that's a little bit overkill. Okay, what are the coordinates? So we know the x coordinate is 2, so then we find f of 2 by plugging it into the reduced one, which equals 5/4. So the coordinates are 2, 5/4. Sweet. If any exist, identify the horizontal asymptotes or end behavior asymptotes. So we have P and Q. P is 2, Q is, oh, you know what? I'm going to change this. P is 1. We're going to go based off of that right there. So P is 1, Q is 1, so they are equal. So it is the ratio of their leading coefficients. So therefore, we're going to write y over equals a over b, which is 1 over 1. So y equals 1. So it says explain how you know. This is probably the only time where I let this information and not a bunch of words explain why. You can put this in words, but if you show that you're comparing the ratio of the degree of the numerator to the degree of the denominator and saying therefore we look at the ratio of their leading coefficients, so we get 1, that's enough for me. What are the zeros of the function? So 0 equals x plus 3. Show your work. X equals negative 3. So this is a 0. If it said intercept, we would write negative 3, 0. This doesn't ask us why, but maybe the test will. So our answer would be non-canceling factor in the numerator. All right. And then what are the domain and the range of the function? Give your answer in interval notation. So this might be hard for you to do without a graph. So sometimes we like to skip and come back. So we're going to go to B, and it says sketch a detailed graph. So get out your information that you just put there. It's almost like yesterday. So I have all this. I have negative 2 is my vertical. Boop, 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 boop. 1 is my horizontal line. Then I have negative 3, 0 is my, right there, that is my x-intercept, I want to point out something just rather quickly for you guys. Sometimes I start counting from an asymptote instead of the y-axis, which isn't right. You should definitely be counting from 0, 0. So if you're ever noticing that your graph seems off, just check that. And then didn't we have a hole at 2 and 5/4, which is 1 and 1/4, so it's here. So guess what? I have a detailed graph without any additional points because there's a hole, I know it's coasting there, and because there's an x-intercept here, I know it's coasting here. So that gives me a chance to go back to my domain and range, and remember, I could have gotten this from my equation for my domain, that it can't equal anything that will make the denominator 0, so it's going to be from negative infinity to negative 2, and then it'll pick up from negative 2 to 2, and then from 2 to infinity. But our graph will also show us that, so negative infinity to 2, and then from negative 2 to 2, and then 2 to infinity. So you remember you have to exclude those holes from your domain and range. So in terms of range though, this is going to be from negative infinity, no holes, but I get that horizontal asymptote at 1, so it's negative infinity to 1. And then I come up to 1, and at 5/4, that was the coordinate of my hole, I have to exclude that y value, and then after 5/4 it goes on forever. Okay, domain and range there. All right, flip it over for our last problem. This is probably a shorter set of notes just because we took so much time and were so thorough yesterday. So this says consider this function. I'm going to factor it x plus 5, x minus 2, 2x minus 1. Nothing cancels, so f of x equals x plus 5 times x minus 2 over 2x minus 1. Identify the vertical asymptotes. So whenever there's a number in front that might be hard for you, so just set it equal to 0. So explain how you know, and this is where we say non-canceling factor. We say 2x plus 1 is minus 1 is a non-canceling factor in the denominator. Okay, does the function have any holes? No. How you know? No factors cancel. If any exist, identify the horizontal asymptotes. Okay, P, Q, P is 2, Q is 1, P is greater than Q, therefore none. Degree of the numerator is greater than the degree of the denominator. And then we could just put a little note here just because it's on our radar that it will have a slant, but that is not a horizontal asymptote. So why will it have a slant? Because P is greater than Q by 1. So I'm going to write that. That would be your rationale. It's not just that because P is greater than Q, it's that P is greater than Q by 1. What are the zeros? 0 equals x plus 5 times x minus 2, so x equals negative 5 and 2, so we have negative 5, 0, and 2, 0. And then domain and range. Again, I'm going to hold off on that till I get my picture. I already know it can't equal 1/2, but you know. So x equals 1/2 is here. It's asking us to sketch a detailed graph, and we did not figure out our slant yet, so let's go ahead and do that real quick so that we get that detailed graph. 2x minus 1 divided by x squared plus 3x minus 10. X squared divided by 2x is 1/2 x. Oh, this looks like it's going to be fun. Minus x squared minus negative 1/2 x. Okay, so that's going to be 3x plus 1/2 x. Right? There's that math right there, plus plus. So that's going to be 6x over 2 plus 7 over 2x. Sorry, 1 over 2, which is 7 over 2x. So you might be wondering where I'm getting that from. It's just falling back on the math we already know, but it's involved in part of another problem, so sometimes we forget about that. So then I have 7 over 2x divided by 2x, which is just a complex fraction because we have more than one. So 7 over 2 times 1 over 2, so that's 7/4. So this is going to be plus 7/4. And I'm going to disregard remainder. So 7/4 is like almost 2. It's 1 3/4. So 1 3/4 is my y-intercept. And then I'm going to go up 1 over 2, up 1 over 2. Maybe I'll go back 1 just to give myself a couple of points to draw a very nice and accurate slant. Alright, so there I am there. Let's see any points we can put in there. We have -5, which is 1, 2, 3, 4, 5. Sweet. That tells me it's coasting along here. And 2, oh, I love it. It's coasting along here. So that's my detailed graph right there. I didn't have to do step 7, those additional points, but I do need to do my domain and range. So the domain, -infinity to 1/2, and then 1/2 to infinity. The only thing it's not being able to equal is the vertical asymptote. And we can also see that from our equation. And then for the range, there's a slant. But sometimes students say, oh, it can't equal this value right here because of the slant. But if you look, the other half of the graph is meeting that. So the domain and range, when a slant asymptote is involved, and only a slant, like there's not additional verticals or anything like that, it's going to be -infinity to infinity. And that is all for 2.6b. Sweet.